We've been talking about addition to sigma star orbitals, and I usually associate that with SN2 reactions, where the leaving group departs at the same time that the nucleophile adds. But when you drop down to lower row elements like silicon, phosphorus, tin, transition metals, that concerted nature of addition to sigma star and the leaving group leaving is lost in most cases, almost all cases. And we've been talking about substitution at silicon, and you have to get ready in this class when we substituted silicon, pretty much every single case you will ever see. We're going to find that it's a two-step process where initially you add to the silicon to make a negatively charged siliconate that's got a trigonal bipyramidal configuration at the silicon, and then in a second step you make the leaving group leave. And so this should be a common theme when you substitute at silicon and replace chloride with oxygen or oxygen with fluoride. And whenever you see the potential, the opportunity to make fluorine-silicon bonds, you go for that because fluorine loves silicon. Let's just move just a short distance here and talk about substitution at silicon when you've got beta-silyl carbocations, beta-silyl carbenium ions. And we had a problem on our problem set that involved this type of a process. We refer to this boring process right here as proto-decylation. So if you have a carbon-silicon bond and you replace that with a carbon H, that's called proto-decylation. It's usually a side reaction. When you go through the trouble of making carbon-silicon bonds, you usually want to do something interesting with it, not replace it with H. So this is a common side reaction in organic synthesis when you use organosilicon compounds. Let's go ahead and draw out the mechanism for this reaction. There's clearly an acid under these conditions. I can't think of anybody who would treat a vinyl silane with hydrochloric acid. But if you did, this is what would happen. You would expect to have this acid. I'll draw it out as a symbolic species, HA. And then we'll go ahead and protonate that double bond. I'm going to start my arrow right here from the middle of the double bond, not from the end of the double bond. And you can't tell where I'm going to put that proton. Right? You start your arrow from the middle of the bond. Let's go ahead and draw that next mechanistic intermediate. I already know where I'm going to put the proton. I'm going to put the proton so that I end up with a beta-silyl carbenium ion. There we go. Look at that. I would never put the proton to make a tertiary system because that wouldn't be beta-silyl. This is beta-silyl carbenium ion. And under the conditions of this reaction, we have water that can form oxygen-silicon bonds in here. So let's go ahead and substitute, because I'm not showing you, I did show you the structure of the product. We have to figure out how to make this silanol byproduct here. And let's go ahead and draw out the arrow pushing that gets us there. First, we're going to take electrons here on the water molecule. Right? You can't just use A minus. That's only for acid base. It's just a symbol for acid base. In theory, you could write Nu with a lone pair, but don't write A minus to attack the silicon because that doesn't indicate nucleophilic character. It's just for acid-base proton transfers. And this is going to be uncomfortable for you when you're first starting out talking about substitution at silicon, because we're going to end up with just a bunch of charges here. That's okay, no problem with that. So I'm going to draw my carbenium ion here. There it is. Stabilize. I hate that bond. That's not a good. Let me try to draw that a little straighter here. Here we go. There's that carbenium ion. All the electron density in this long nucleophilic carbon-silicon bond donating into that carbenium ion. Let me put the negative charge. It's not just silicon. It's a siliconate. That means all the bonds to silicon are even more nucleophilic with that negative charge on the siliconate species. And now I have this oxygen atom over here with 3 bonds. That's an oxonium when you have 3 bonds to oxygen. Look at all those charges. I'll circle them just so we can see them. You know, if you're uncomfortable drawing all those charges out, get over it. Right? That's just the way these species look when you do proto-decylation and you have to get that silicon off of there. We're going to see a bunch of mechanisms in this class that have this kind of combination of charges. Now, we have to make a choice here. Are we going to use these electrons and form the double bond in our alkene, or are we going to deprotonate first? And I'm just telling you, you need to deprotonate first here. You wouldn't have been able to rationalize that. But proton transfers are fast. And in this case, it's so fast that should be the preferred step. And once we deprotonate that oxonium ion, it's easier for the silicon to show its full nucleophilicity here. Let me go ahead and draw out that next intermediate. The next intermediate is still at siliconate. And now because there's not a positive charge next door, now that siliconate can really be nucleophilic here. And now we're going to make that silicon-carbon bond that kind of lean over here and then give its electrons to that carbenium ion. And that's what gives us our final alkene and our silanol byproduct. Okay, so get used to this kind of combination of charges. Siliconate, negative charge on silicon, 5 bonds to silicon, no problem. You can have 6 bonds to silicon. Silicon is not a second row atom like carbon. So you just have to get used to these combinations. And why are all these charges okay? Notice if you sum up all the charges in this species, it's never more or less than 1. Right? We don't have an overall charge of +2. If I start to generate molecules where there's a net charge of +2, like plus, 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 and then a minus charge, that's not good. You need to be very wary if you're starting to generate species that have nearby formal charges that sum up to more than 1 or -1, or less than -1. Okay. Let's keep going talking about addition to sigma star orbitals. Let's come back to carbon. So again, I said when I think about addition to sigma star orbitals, I'm normally thinking about second row atoms, and carbon is really the only one that's important. We don't do SN2 at nitrogen or oxygen. So I'm going to go ahead and show you the relative rates. This is this first comparison here between these 3 alkyl halides. This is a series that we commonly introduce people to in introductory organic chemistry courses. So all of you should know that if you do SN2 type substitution reactions, that it is faster to substitute on primary alkyl halides, like this one right here, versus tertiary. That should be very slow. And it's not just how slow this is, it's because the more CH3s you add, the more likely it is to have competing E2 elimination. So it's not just that it's slower, it's you make the side reaction, which is elimination, much faster. There's more H's on those alkyl groups that are beta to the leaving group. Let me go ahead and give you some relative rates here so we can be a little bit quantitative. So the relative rate for SN2 substitution, concerted SN2 substitution, relative, I'll assign a relative rate of 1 to this tertiary alkyl X. X could be chloride, bromide, iodide, H2O plus, doesn't really matter. Secondary is 15 times faster when you've got fewer alkyl groups on that carbon atom. It's harder to add to a carbon center, do an SN2, when you've got more alkyl groups. And finally, when I get over here to the alkyl, primary alkyl halide, SN2 starts to look a bit more reasonable, right? 600 times faster. And it's not simply that this is slow. Again, the problem is not simply that this is slow. The problem is that there's H's on these alkyl groups, and you'll end up just getting 100% elimination. That doesn't get slowed down when you add extra steric hindrance there. Now, let's move one over. This carbon atom that is next to the carbon atom that is next to this leaving group right here, we call that the alpha carbon. Carbon next to X is the alpha carbon. Carbon next to the leaving group is alpha carbon. Carbon next to the leaving group is the alpha carbon. If you add substituents to the beta carbon, it also slows down the rate of SN2 substitution. So if I come over here to this beta carbon, right, these are both of these species here are primary alkyl halides. Now, it's got a pretty similar rate when you compare propyl to ethyl. I'm going to go ahead and give you the relative rates here. The relative rate for substitution at this propyl group, where I've got one extra methyl group on the beta carbon, that's pretty similar. 600, 400, those are right in the same ballpark. We're usually interested in factors of 100 or 1,000 or 10,000. That's the kind of thing that gets us interested, right? 600, 6 to 4 or 3 to 2 or 1.5 to 1, those types of things I don't expect you to be able to rationalize easily. But what happens if I put a second alkyl group on this beta carbon here? I start to branch that beta carbon even more. Well, now it starts to get even slower. So instead of 600 to 400, now it's got a relative rate of 100. So it's still faster than trying to substitute it a T-butyl. Let's take a look at what happens when I add one final alkyl substituent to this beta carbon right here, this beta carbon right there. Boy, SN2 is so sensitive to steric effects. when I look at the relative rate for substitution here with a nucleophile, that is really hard. That's really hard for a nucleophile. I can't even fit my electrons in there. And the rate is 0.01. It is 100 times slower to substitute when you've got beta branching. And we call that center a neopentyl center. Let me go ahead and give that a name there, because you should look for this when you try to do substitution. That's called, well, that center is not, this whole group is called neopentyl. This is called a neopentyl group. Neopentyl. Neopentyl means you've got like a quaternary center 1 carbon over. It's worse than trying to do SN2 substitution at a tertiary center. So if you ever learned that you're not supposed to do SN2 at a tertiary center, neopentyl should look way worse to you. There is no way that this nucleophile can wiggle its way in here. There's just no way that a nucleophile can get in here without bumping into one of these methyl groups. Those methyl groups are right in the trajectory, kind of preventing any nucleophile from getting in. So the substitution at neopentyl centers is notoriously difficult. I'm showing you an example down here where somebody tried to do a synthesis of this natural product called nitiol. They spent most of their graduate career working out a 30-step synthetic route to get to this intermediate. And the thinking was, well, I'm sure maybe we can find some way to make some nucleophilic bond here and then do some substitution. But if you look next door to that X group, it's a quaternary center. That's a neopentyl center. In fact, they were never able to get this substitution to work, and they had to abandon the whole route and all the work that went into that. You know, it's very hard to substitute at neopentyl centers. I don't want to try to put these people down. There's other strategies you can take when you're doing synthetic organic chemistry. You can take your bromide and convert it into a Grignard reagent, so it's a nucleophilic bond, and then you're using the bond as a nucleophile. None of those actually worked here, but the SN2 strategy certainly didn't work, and I'm sure they knew that that was just a Hail Mary pass when they started off the synthetic route. Boy, it's so hard to substitute at neopentyl centers. Okay, so and hard to substitute at tertiary centers. Let me go ahead and show you some observations here that the first one here you should know, right? If you try to do SN2 displacement here, don't expect that to work. It's slow. So what can you do to speed it up? Well, you use a more powerful nucleophile. Problem is, more powerful nucleophiles are also more powerful bases. You're just going to get elimination by attacking the H's here and end up making alkenes. And usually you want to make bonds to carbon, not simply fragment off leaving groups. So don't try to do SN2 at these centers. So it's, if you go to a more reactive nucleophile, like instead of water, go to an alkoxide, you just get E2 elimination to make an alkene. In that case, you just get this, and you haven't made any new bonds to that carbon atom when you do the elimination reaction. That was probably the starting material for making that alkyl bromide. Or maybe if it's too basic and you don't want E2, you can switch to just a neutral alcohol. Well, that's not going to be very fast. You're not going to be able to add a weak lone pair on just an alcohol and do an SN2 reaction. Maybe you could heat it, but as soon as you start heating it, you'll end up getting carbocations, and you'll just get a mixture of different products that go through the carbocation. See, via some tertiary. Let me make that T-butyl via some tertiary carbocation like this. So you're kind of stuck there with an alkyl halide. Now let me show you another observation that we can try to fit in here. If you take strained rings, like this epoxide here, well, that's much easier to make a carbon-oxygen atom act as a leaving group. To make an O- act as a leaving group in an SN2 reaction. We can do an SN2 reaction with an alkoxide leaving group in this case because that bond, the ring, is so strained. That relieves ring strain right there. Right? Notice how you don't substitute at the tertiary center in this SN2 reaction. You don't add to the tertiary center. You add to the primary center, and it works here because of that ring strain, allows you to open up and have an alkoxide act as a leaving group in this case. Now, let me just show you something that may seem inexplicable, but there's a generalization here that's useful. That is, if you do this same kind of substitution of the epoxide under acidic conditions, that's a different scenario. Because if you substitute an epoxide like that under acidic conditions, you don't have alkoxides under acidic conditions if you're throwing in HCl or sulfuric acid, right? If you've got conditions that are acidic enough to protonate the epoxide, then all of your OR groups, ethanol groups, or any other nucleophiles are going to be neutral. You won't have any O minus. If you have enough acid to protonate the epoxide, then that acid's going to make sure all the ethoxide is protonated and is neutral ethanol. Now, when you protonate epoxides, the regiochemistry changes. When you protonate epoxides and open them under acidic conditions, you don't get attack at the primary center, you get attack at the tertiary center. You get SN2 ring opening at the tertiary center. That is preferred strongly. And this is a general theme. If you take aziridinium ions that are also strained, you don't get attack at the primary center, they open at the tertiary center. If you take strained three-membered rings, this is called an episulfonium ion. We'll talk about these later. The name is kind of like epoxide, but we call that an episulfonium ion. You attack at the tertiary center. You don't attack at the primary center. You attack at the... If you take three-membered rings, here's one way to depict pi complexes between olefins and palladium. You can draw these as Pilatus metallocyclopropanes. You attack at the more substituted center. Man, that's gold. That rule is golden. Mercurinium ions in oxymercuration reactions. We don't teach these anymore because they don't want to use mercury in the labs. It costs too much money to dispose of safely. But they used to do these experiments all the time in the 70s in sophomore organic chemistry labs. You attack at the more substituted center. So, attack at the primary center if you have a neutral three-membered ring. But if you have an onium ion three-membered ring, you attack at the more substituted center. Yeah, I see some questions coming up. Yeah.
What kind of nucleophile would work best in this situation? Or in those situations?
Well, it's a little... So the question is, what nucleophile would work best? This is a little tricky because if you make the nucleophile too good, you're simply going to deprotonate. So water would be a typical one. We don't have to worry about water catching all the protons here. Amines, no good because amines would catch the protons. So you can't have strong nucleophiles in these situations. Water and alcohols are the common ones here. Here it could be chloride, could be other amines, could be azide anion, could be thiolate anion, could be a phosphine anion. I don't think an allylsilane is nucleophilic enough to add to that. Same here, episulfonium ions. These you can have ammonia. Notice I have no proton here on the sulfur. You can have ammonia in there. It would easily be compatible with those conditions. Here with the palladium, water would be a common one. You also have softer nucleophiles. Somebody else had a question?
Yeah, so would it be safe to say that smaller nucleophiles work better at attacking the tertiary?
You're not going to make it small enough. So some of the slimmest and trimmest nucleophiles that I know of that really are good because they don't have much steric hindrance would be something like cyanide. Man, that thing is like an arrow. Just no steric hindrance. Still not good enough. You still are going to get E2 elimination if you try to wiggle a cyanide anion in there. It's not going to make it. Azide anion, again, linear. Great nucleophile for SN2 reactions, but you're still not going to get this azide anion to work at that tertiary center. So you just can't make it unhindered enough to make it good to substitute at tertiary centers. These systems down here, though, no problem attacking at tertiary. That's the bias. Somebody else had a question.
Actually, kind of like about the last slide, I'm kind of just wondering why is it slower to do it with the beta on the beta carbon instead of the alpha? Like I would imagine since in the alpha carbon, like it's directly there, it would be slower because there's like a one carbon gap.
Yeah, it's because of the trajectory. There's a sigma star orbital sitting out at the back end of this. Let me see if I can draw that in. The question is, why is the neopentyl slower? There's a sigma star orbital on the back end for this carbon X bond, sigma star. And you can wiggle in there and overlap with that. But if you try to overlap with that sigma star orbital here, there is no way you can do that. Right? I'm drawing it as Me, but it's actually CH3 with H's on there. And there is no way that you can wiggle your way in and overlap with that sigma star without directly bumping against the CH3 group, or even, some cases it could be larger. There's just no way. And you couldn't have rationalized that difference. I had to tell you which one was faster and which one was slower. But now that I've told you, be on the lookout for neopentyl centers. Yeah?
Oh, on that note, what was that next product on the bottom? So, that, like the
What was the product? I think the question is, what was the product that they got in these cases?
Well, my question is like, what is that compound next to it?
This compound over here?
Yeah, because you said that mechanism couldn't act.
Oh, I'm sorry. Here's what I meant to say. Or this is what I meant to say, is they never got this. Nothing they ever tried allowed them to get that macrocyclic ring. Yeah, so, and again, it's hard to do an SN2 at this center. But you can change bromide into a magnesium chloride, and now you're talking nucleophile. That doesn't have that problem. The trajectories are different, right? If I take this, MGBR, now you don't have to attack here with a nucleophile. Now you're talking about that, and that's not sterically hindered. So they knew that going in. It's just a good plan. I'm sure they didn't expect the neopentyl substitution to work, but they had other backup plans. Just turns out those didn't work. You very rarely, it's hard for me to find examples of things that don't work in the literature because most people don't report things that don't work. So sorry if I couldn't come up with a better example than that one. But okay, let's keep going here. We're talking about substitution, addition to sigma star orbitals to do SN2 type substitution. And let me go ahead and talk about the effect of a neighboring pi system. I'll show you first kind of a not so obvious effect, and that is if you do SN2 next to a carbonyl. So next to a carbonyl group here. If I try to do SN2 next to this carbonyl, that SN2 reaction is faster than if there's no carbonyl there. The carbonyl speeds up this reaction. So it speeds up SN2. It accelerates SN2 reactions, and that is not obvious. It's not obvious, I don't think, that a carbonyl would accelerate the rate of an SN2. Let me give you some numbers down at the bottom here to help us understand what's going on, right? The general trend. What you observe if you try to do substitution down below here, let's go ahead and compare some relative numbers. If I look at the rate of SN2 substitution of this alkyl chloride bond right here, and I'll assign that a relative rate of 1. When you put a pi bond next door, it gets faster. It is faster to substitute through SN2 reactions allyl chloride than it is to substitute just propyl chloride, right? Even if the sterics are about the same, it's just faster to add here at this carbon atom. Now it is true also that allyl chloride undergoes SN1 reactions faster, but I'm talking about SN2. SN1 gets faster, you make allylcarbenium ions. SN2 gets faster when you have a double bond. Allylic systems substitute faster. I don't have benzylic chloride here, but benzyl chloride substitutes faster through SN2. Right? We're not talking about carbocations, we're just talking about SN2 reactions. What is not obvious is when you put an electron withdrawing group like a cyano group here, that's electron withdrawing, it gets even faster. Not by a little bit, but by a lot. Wow, 3,000 times faster than propyl chloride. What is up with, there must be something that we didn't talk about in detail here. When I get to an acetone or a carbonyl next door, it could be an ester, it could be a ketone like this. It's the same idea. I think it's, 35,000 here? 3,000, 35,000, that's interesting, but there's something, there's something going on here with having pi systems that are electron acceptors next door to the SN2 site where you're attacking. Why is SN2 faster when we put these pi acceptors next door? Let me come back up above here, and let's take a look at this picture of the transition state. If I drew out the transition state for this substitution process, let me just put a little symbol here that we're talking about the transition state. So in the transition state, you're going through a trigonal bipyramidal structure. So when you add through SN2 reactions, you invariably have nucleophiles with anionic character. You should be used to that. Maybe chloride, hydroxide, something, a thiolate anion. They usually have anionic character in those. And there's 2 electrons in this orbital, the lone pair orbital. Now, the leaving group usually also loves to have anionic character. You like to have leaving groups that are electronegative. Chloride, H2O plus, things that are electronegative. So in that transition state, you'll end up with a situation where you've got 2 electrons in this bond over here. There's 2 electrons in the bond that's leaving, and there's 2 electrons over here in the nucleophile that's adding. Where do those electrons go in the transition state? It's like it turns out that they end up in this orbital. Let me try to use a different color here. They end up in this orbital that is like a p orbital in the transition state. It's got p-like character, right? As my nucleophile comes in and interacts with sigma star, you'll end up with these extra electrons. Those 2 electrons end up in this p orbital. And then let me make that hashed here. So you end up with this filled p orbital in the transition state. Boy, lone pairs don't like to be in p orbitals. They like to be in low-lying, that's not a good orbital for a pair of electrons to be in. They want to be in maybe sigma or pi or something like that. So you got this pair of electrons in this p orbital. What can we do to stabilize this transition state? And now you see the beauty of having a pi system next door. A CC pi, even better, a CO pi. Not just pi, but pi star. If you put a pi star acceptor orbital over here that's good at accepting electrons, now you can get donation from in the transition state, from that p-like orbital in the transition state into pi star. Alkenes aren't quite as good at that because it's not as easy to add to a CC pi, but it's better than nothing, right? It's better than nothing. So you even get a little bit of stabilization of the transition state, faster reactions, even with an allyl or benzyl group there. It's better than having no pi system next door. So if I wanted to do SN2 reactions and I wanted it to work great, I would take one of these 2 compounds here, right? What's the best for SN2 substitution? It's not a primary alkyl halide. It's putting your leaving group at an unhindered center that is next to cyano or a carbonyl ester ketone. That's how to get, if you just want to make some sloppy bond and you don't care about the functional groups and you have to use SN2, boy, this is the best game in town right here. Putting carbonyl or cyano group. But usually you do care about the functional groups that are attached at the centers where you're making bonds. Okay, so nearby pi centers, benzyl, allyl, next to ketones, you get faster rates of SN2 substitution reactions. Now, I want to spend most of my time talking about good SN2 reactions instead of crappy ones, but let's go ahead and talk about a crappy SN2 substitution. So we've been talking about SN2 substitution at sp3 hybridized centers like this. That's the way SN2 you should think about it, right? Through trigonal bipyramidal transition states. What about this though? What if I had a vinyl halide, a vinyl iodide, or some other type of vinyl group on there? Can I do SN2 at this type of a center? Maybe. It's not impossible. But if that's the first thing you're drawing out, you need to rethink that, because that is not. Don't get used to that. How are you going to generate a trigonal bipyramidal structure by doing that? You're going to end up with a planar carbon atom. There was a famous estimate that somebody estimated that if you just took methane and made it planar, it's 100 kcals per mole higher in energy than tetrahedral methane. You can calculate the relative stability in factors of 10 if you're good at dividing 100 kcals by 1.4. So what about this case? This is a substitution reaction that can occur. You can take nucleophiles like hydroxide. You can take thiolate anions or in this case, sulfide anion, and add those, do a substitution of alkyl chlorides. That's possible. You can do those. This came from a gas phase calculation, so the molecules are very simple. But when you look at the mechanism for this substitution, it's not necessarily the way you think it's going. Right? If you're thinking it's going through an SN2 process, that's not what's happening here. The preferred mechanism for this reaction is this. And you're probably thinking, well, that's insane. You probably have to have high temperatures to add to an alkene and make a carbanion. That's right. This is not a substitution that would occur at low temperatures, right? And the product wouldn't be stable as an enol, but if you use an alkoxy group, enol ethers are stable. So this is a 2-step substitution process. Nowhere near as good as adding to an acyl chloride, right? That's the mechanism for this substitution. So you can substitute at sp2 centers, but doing direct SN2 substitution at sp2 centers, vinyl halides, there's no way to substitute through SN2 in a benzene ring because you can't get to the backside. So this is a kind of a fairly different reason why it's not possible to do SN2 here. So, right, if you had some sort of a nucleophile here, right, this is now a world of hurt trying to fit yourself inside that benzene ring. But But even vinyl halides, don't try to do SN2 substitution. Do it through some other mechanism like addition to pi star. Okay. There's this thing that you will see in the literature, and you will be tempted to try to draw out these mechanisms. I want to talk about something called an SN2 prime substitution mechanism. SN2 prime. See that little prime there? It almost gets lost. And here's the deal. If you have this sort of an allylic halide and you do a substitution, how would you know, if you look at the product, how would you know here with this new bond right here, how would you know whether that went through SN2 or maybe it went through an allocarbeniamine, an allocation, right? If you saw substitution occurring at both ends, maybe you did put a deuterium label at one end and not at the other. You might find that the nucleophile is adding to one end versus the other. Might get a mixture. Let's just put a C13 label here, like just a pretend C13 label here. You might end up finding that whoops, but that's not well drawn. If I just put a little dot here, suppose I put a label there, and then finally we found that half of the nucleophile had that label at the far end, away from where the nucleophile was. So there's more than one possible substitution route for these allylic systems. There's SN1 type substitution mechanisms where you make a carbenium ion, and then there's SN2, but there's another possibility here. And how do we rule out this possibility where the lone pair simply attacks here and then pushes out the leaving group in one step? That's called an SN2 prime substitution mechanism. And it's possible, but it is almost certainly not likely in any case you're ever going to see. So if you want to propose this kind of SN2 prime substitution mechanism of an allylic bromide, an allylic chloride, an allylic tosylate, let me show you what you need to do. You need to be skeptical if anybody tells you they did that. You need to provide some solid evidence, because SN2 prime, just with all things equal, is 1,000 times slower than SN2. Why would a molecule go through a pathway that's 1,000 times slower? That's not normal. You have to somehow stop the SN2 by rigging your substrate every possible way in order to force it to go through an SN2 prime. I'm going to show you one example to show you what kinds of gymnastics you have to go through in order to get something to go through that SN2 prime mechanism. Here's a very clever piece of work where somebody tried to slow down the rates of SN2. Look what they did. They put this beta branching down here, right, to slow down. They're trying to get a little closer to a neopentyl center to really screw over the normal SN2 route. And it's always axial. This one methyl group that's down is always in the way of the preferred transition state coming from the backside. So that was a trick that they used. It's cyclic, so they can tell. They can tell which face the nucleophile adds from. They were able to get this reaction to go even though they've ruined the SN2 process. What else did they do to ruin SN2 and make it really slow? Well, they used a crummy leaving group, right? They didn't go with tosylate because they don't want to get allocations. They didn't go with chloride. They don't want allocations. They want SN2 or SN2 prime. So they've got an awful leaving group that can't make allocations. They've put beta branching to slow down the SN2. So sterically, really, the only good possibility here is this one, and it still wasn't a good reaction. They had to use the nucleophile as their solvent to bring up the concentration. 10 times higher concentration, 10 times faster. 100 times higher concentration, 100 times faster. Still wasn't good enough. They had to boil it at 130 degrees. And that still wasn't good enough. They had to wait days for this thing to work. So this was not a good reaction. Right? If you slow down every single possibility, maybe you can get to an SN2 prime reaction. Now, how did they know that it was going through SN2 prime and not some allocation thing? Because in the product of this reaction, the nucleophile approached only. The only product you get is where the nucleophile approaches from the same face as the leaving group. Why does that happen? Why does the nucleophile have to approach from the same side as the leaving group if you're doing an SN2 prime? If you look at the orbital overlap here, right, if you're trying to get some sort of a nucleophile to add to this double bond, you're adding to pi star. So let's go ahead and draw out this pi star, this pi star orbital. You've got some sort of an interaction between the nucleophile adding to pi star. And if you draw out the orbital phasing for a pi star, right, you have, if you have the same phasing as the nucleophile, I've put that in dark green here, that means the electrons are going to come out on the opposite face. And when those electrons come out on the opposite face, they will be aligned with sigma star for the CX leaving group, CX, to attack and make it leave from the same face. So this is just a requirement of orbital symmetry. If it's an SN2 prime reaction, the nucleophile must approach from the same face as the leaving group in order to get those orbitals to work out. This idea that when you add to pi star that the electrons appear on the other side, there's nothing new about that. Let me just make that an X as my nucleophile. There's nothing new or exciting about that idea. But you'll see, I think you'll see this in other cases. So if you add to pi star, doesn't matter whether it's a carbonyl or an alkene, the electrons appear on the other side of the CC bond. You'll end up with a system that looks like this, with those electrons on the opposite side. That's supposed to be a lone pair there. And that makes sense because that's the exact opposite of making it act as a leaving group. Because if you try to make these push out the X leaving group, you want this orbital to be aligned with the backside to go backwards. So there's this kind of mirror symmetry here going forward and backwards. When you add nucleophiles to the top of the pi, the electrons appear on the bottom side of that pi system. Wow.
How well does this SN2 on sp2 carbons work? Like, what's the percent yield of the products?
In this case,
Yeah, in this case or in any.
I apologize, I didn't look up the yield. You know, they just needed to get a little bit of this so they could show, based on the stereochemistry, it proves that it went through SN2. You know, they can be okay. The yield in this case, I seem to remember was pretty good. But what does that mean? 90%, 80%? Right? They're just trying to stop SN2 and they're trying to stop SN1 reactions. But the yield can be pretty good if you stop those other alternatives and are patient enough to wait. Another question.
Intermediate more stable than typical SN2 compared to SN.
Say that again. Is the
Intermediate species more stable in an SN2 prime or no?
Well, there's no this is a concerted process. The question is the intermediate more stable? This is a concerted reaction. I didn't finish the arrow pushing. The arrow pushing goes like this, all concerted. So at the same time that you're adding, you're weakening the CO bond. So it's a SN2 prime is a concerted process that doesn't go through a carbanion intermediate. Sorry, I didn't make that clear. All right, I am worried that we have run out of time to move on to our next. Let me just make sure how badly I've misused our time here. We're still not done with SN2 type processes. When we come back on Friday, we're going to talk about more cases where you add to sigma star. But these will be slightly different. We're going to be using nucleophiles that are built into the molecules, and they will be non-obvious examples. Okay, so I already told you about how electronegative substituents nearby can slow down the rate of SN2 reactions. But you've got to be very careful to look at which parts of the, I'm going to go ahead and keep going just like this. So I'm giving you an example here of a carbohydrate type molecule. This is a typical intermediate in carbohydrate hydrolysis. It's the same as the mechanistic intermediate when you do glycosyl transfer reactions or glycoside hydrolysis. When you put a good leaving group here, the neighboring substituents impact the rate at which this group leaves. Now, you know, there's obviously a lone pair up here that can help to make that group leave. Right? That group right there can help push out that water leaving group. But what about this hydroxyl group over here? Right? When you put a hydroxyl group that is not right next door to the sigma star orbital, right? The lone pairs on this OH are not very nucleophilic, and they're not the same distance away. So I can push out this leaving group using these lone pairs and end up with a CO double bond. But this bottom OH over here slows down the rate at which you ionize. It slows down the rate of substitution via SN1. Slows, let me just say, slows SN1. So it's going to slow down the formation of carbenium ions. It's going to slow the ability of that to generate an empty p orbital. And I already told you that what you couldn't have rationalized or known is that the lone pair in here is so non-nucleophilic, I don't want to really draw this in, is that you don't get participation. I'll just write no. Don't do that. You can't use the lone pairs on that OH. Nitrogen amines, yes, but not OH lone pairs. They're not nucleophilic enough to bend over and make a strained ring. You'll see these effects of that beta OH group in other types of molecules. I'm giving you an example here of RNA versus DNA. RNA, if you look at rates of depurination or the loss of the base from these groups, how quickly do you lose the base and undergo mutations? It's slower in RNA. That OH group slows down the rate of SN1 ionization, if I just write this out as SN1. Right? The OH group of RNA. Now, RNA overall is way less stable. That's a completely different effect. If you've ever worked with RNA and DNA in the laboratory, you know that this OH group is bending over and hydrolyzing the phosphate intramolecularly. That's a completely different effect from losing the base, that X group, through an SN1 reaction. There's a common set of intermediates, nicotinamide, adenine dinucleotide. They serve as hydride donors. Here's one form, NAD+, where it makes this pyridinium group. When you donate a hydride from this carbon, it turns this into an aromatic pyridinium, which is a good leaving group. Boy, that's not so good, right? You don't want your NAD+ to fall apart. But if you have an OH group here, like you do in NADH and NAD, that OH group slows down the rate of that ionization of NAD+. So electronegative groups slow down that. It slows that SN. If X is equal to some electronegative group like hydroxyl, it'll slow down the SN1 ionization. Okay, so oxygen slows down the formation of carbenium ions next door, a substitution via SN1-2 type mechanisms. But I mentioned to you already, if you have nitrogen lone pairs, they can accelerate the rate at which you push out leaving groups. And they do it through what looks like an SN2 type process. Look at that. Unfortunately, this is still a clinically used anti-cancer agent. Unfortunately, I say, because it is brutal. It was developed 100 years ago. Why they still use this, it completely mystifies me. But the mechanism by which this alkylates DNA and kills rapidly dividing cells is just what I'm showing right here. You take that nitrogen lone pair, and it helps push out the leaving group, and it makes this strained aziridinium ring that loves to be close to the phosphate backbone of DNA. Imagine sprinkling a bunch of those aziridinium cations near the anionic phosphate backbone of DNA. And so the DNA bases, particularly the N7 position of guanine, will come back in and attack. And then the same thing happens on the other side, right? There's two leaving groups here. And then once you regenerate this lone pair, I don't have a lot of room to stick that arrow in there. Once you regenerate the nitrogen lone pair, the same thing happens on the other side, and you cross-link strands of DNA. Rapidly dividing cells are very sensitive to cross-linking of their DNA. They're checking during the checkpoints. If they can't pull the strands apart to make copies, they commit suicide. So these reagents kill all rapidly dividing cells. They don't kill cells like muscle cells that aren't dividing. And unfortunately, your hair follicles are rapidly dividing, your gastrointestinal lumen is rapidly dividing, your fingernail cells are rapidly dividing, your immune system is all rapidly dividing white blood cells. These reagents also kill all of those cell types as well. Now, it doesn't have to look like this mustard agent. This is called a nitrogen mustard, this class of reagents. It can have complex structures like this one down here. We had a problem on our last problem set. I can't remember whether it was in the challenge problems or not. They look very much like this. You can have other nitrogen lone pairs, and as long as they're 3 atoms away from that center, you can use the nitrogen lone pairs to help push out the leaving group. Not oxygen lone pairs, but amine lone pairs can do that. And so this will generate an aziridinium ring. Let me switch to a black pen here. That will generate an aziridinium ring. That's not that different from the one I showed you just up above there. Look at that aziridinium ring right there. That's ready to undergo substitution. If you just heated this, or if there's a chloride anion, if you just all you did was heat it, the chloride would come back in and open that back up. It's much more interesting if you have other nucleophiles present, You could have other amines, you could have DNA, you could have a protein thiolate backbone or on the backbone of the protein, just some other nucleophile that's compatible with these conditions. Now when the nucleophile comes back in and adds, the nucleophile can come back in and add right from the same position where the chloride left. And it'll generate the same kind of substitution pattern that we started off with over here. Right? Well, it'll look for all the world like all we did was a simple SN2 substitution. And you wouldn't have known that it went through an aziridinium ring. That looks like all it did was SN2. Right? You have no idea. Did that do something special? The way you know it did something special is you'll get a second product out of this reaction that looks like this. Right? There's also a possibility to attack over here on this more substituted carbon. In fact, that's a little bit faster than attacking at the primary CH2. And so the major product in this reaction, whoa, let me try to draw this a little better. It's supposed to be a 6-membered ring, and I'm not doing a good job of drawing that. Yeah. The major product in this process is going to have the nucleophile over here at this position. And this SN2 reaction occurs with inversion of configuration. And so if this H is up here and here, that H would still be up because you're attacking from the bottom face of the ring, but the leaving group leaves with inversion. So you don't change when you do a double inversion process like this, you don't change the overall stereochemistry when you do double inversion processes, 2 consecutive SN2 type processes. Okay, the last thing I want to tell you is we don't have a good language to describe these processes. We're kind of screwed here. Let me go ahead and talk about a term that I've used throughout this course, and that's SN2. I've also used the term SN1. Let me show you an example of a classical SN2. You take hydroxide, you push out a leaving group. That's called an SN2 reaction. And we know that's an SN2 because the rate depends on the concentrations of both the nucleophile and the electrophile. 10 times more nucleophile, it'll be 10 times faster. 10 times more electrophile, you'll generate product 10 times faster. That makes sense. That's SN2. For kineticists who love to talk about concentration effects, that makes sense to call that SN2. Let's talk about this other process over here, where I push out a leaving group using this lone pair. Is that SN2? Well, I mean, maybe I could have just drawn a resonance structure that looks like this and not use the lone pair, and then it's obvious, well, that's an SN1. I just have the carbon-chlorine bond leave. It's not SN2. But what about this? I have an alkoxide over here, intramolecularly, and I push out the leaving group. The rate of that reaction only depends on one molecule. That's an SN1 process, by definition. It doesn't depend on a second molecule. Same thing if I do this aziridinium trick. That also the rate does not depend. These terms SN1 and SN2 were designed by kinetics people who can see, well, there's no other species here in my rate equation. Therefore, these are all SN1 processes. The only thing that makes these have a common theme here is that all of these are concerted displacements. So if you want to use some sort of language and be really precise about what you're saying, we have to call these concerted displacements. All of them. You can't call them all SN2 reactions. We have to call them concerted displacement reactions. Otherwise, you're saying the wrong thing. If you call any of these SN2 processes, you're misstating the mechanistic description. So, sorry that our mechanisms were defined by kineticists who care about concentrations. That's kind of not good terminology for us. All right, thank you for giving me a little extra time. We'll continue on Friday with more of these concerted displacements that occur intramolecularly.